Well, interesting thing. We know that if you got a beam of electrons moving along and you got a magnetic field, for example, a magnetic field into the board, okay, then we know that they're going to be deflected. Okay. And so what direction? Well, we know that the the force is going to be QV cross B. So right hand rule, okay, if V is that way, if B is into the board, V cross B is upwards. Now, if these are positive charges, they are deflected upwards. If they're negative charges, though, they're deflected downwards, because negative of up is going to be down. And so that's the what's going to be happening here. Now, we'll get more about this later, because this turns out to be an interesting thing. This was one of the things they discovered in the early days of activity, is that we have radioisotopes that are producing radioactive something, and they didn't know what radioactive was, but there was something being produced radioactively. And so what they did was they applied a magnetic field, and they noticed that some of these things deflected upwards like this, some of them deflected downward sharply, and some went straight. And so they call the ones deflecting upwards alpha particles. The ones that deflected sharply downwards were betas, and the ones that went straight were gammas. All right, so here we have the idea that we got magnetic deflection. Okay, well, it actually gets a little more interesting than that. Okay, because what can happen is that if we have magnetic field like this, so magnetic field into the screen here, and I've got a charged positive particle here, it's moving that way, so it has a force this way, so that means it ends up going this way. Well, now it's moving, so it still has a force that way, so it goes this way. Force this way still goes like, so what happens is the force is always perpendicular to the motion. Well, you know from physics 1, a force that is always perpendicular to the motion changes the direction, but not the magnitude or the velocity. And so that would force the thing to go in circular motion. In other words, it is centripetal force. So the magnetic force become a centripetal force. And so look at it, we know centripetal force from physics 1 is mv squared over r. Well, the magnetic force, the magnetic force is going to be QVB, assuming that V and B are perpendicular to each other. If they're not, we'll worry about that later. And so if we set the two equal together, QVB equals mv squared over r. Well, what we find is that V cancels one of those V's, and so we can say that R is going to be mv over QB. So that's the radius of curvature right here. And so we call this cyclotron motion. So this would be the cyclotron radius. All right, so now we have an idea here that we have things going around. Now that actually turns out to be useful in a variety of different aspects. And so we'll get to those in a moment. But if you're going in cyclotron motion here, okay, so magnetic field into the board, okay, or into the page. Okay, if it's a positive particle, it's going to be going counterclockwise. If it's a negative particle, it is going clockwise. Okay, V cross B. If it's moving in this direction like that, okay, then V cross B is that way. Okay, now that's if it's positive. If it's negative, V cross B is pointing in the other direction, so it's going to spin in the other direction. Okay, so we know it's going around here. It's going some velocity v, and it's going around a distance of 2 pi r. So the time that it takes to go around, the cyclotron period, is going to be the distance 2 pi r over v. Well, r we know is m, so this is 2 pi times mv over qb times v. The v's cancel. So the period it takes to go around is 2 pi m divided by qb. Okay. The frequency is 1 over the period, so the cyclotron frequency would be qb over 2 pi m. Now notice something really interesting has happened. The period and the frequency no longer depend on the velocity. It doesn't really matter how fast these things are moving. They still take the same length of time to go around. Now, the size of the orbit, the radius, does depend on the velocity. So these are different factors here, the cyclotron motion. Now, this actually turns out to be a very interesting sort of thing. It means that you could actually make something that oscillates at a particular frequency, and all you're going to do is figure out what do you need to make it oscillate at that frequency, and then you can do that, okay? And the period tells you how long it takes to go around, and so for cyclotron machines, there's actually a machine called a cyclotron that has a magnetic field in it, and so what happens is you have particles you dump in here, and they're going around. Okay, and then what you can do is, you know that if you have an electric field, the electric field does work on it and speeds it up. Now, here's the interesting thing. A statement is frequently made, magnetic fields don't do work. Now, explain that. How could magnetic fields not do work? Well, you know that work is the integral of f dot dx. Well, dx is the distance around the motion here. But we know the magnetic force is always perpendicular to that. So if you have a dot product of things that are perpendicular, that's 0. So magnetic fields don't do work. Magnetic fields can change the direction of motion, but they don't speed it up or slow it down. They just change the direction. So how would you speed up this particle if you wanted to speed it up? Well, what you do is you have some metal plates here with an electric field. So every time they go by, they speed up. Now you can start increasing the magnetic field to keep them going around at the constant distance until they are going the speed you want them to be. Once they're going the speed you want them to be, then you can send them off and do things with it. Again, for proton therapy and cancer treatment, this is exactly what they do. Is they have a cyclotron and they can speed up the protons in the cyclotron until they're going at appreciable speed of the light, and then you spew them out at this specified energy, specified velocity, and then you can target tumors with that. There's also used materials characterization and other sort of things. Very large cyclotrons, what you do is you have magnets placed around a giant loop that is miles or tens of miles across, and so each magnet is in sync here with and so what happens is you have in one spot in this giant orbit you have an electric accelerator that speeds things up, and the particles go around this way, positive particles that way, negative particles this way, and you have them going around, and every time they go through here, they go faster, and so you have to increase all the magnetic fields in sync so that they stay in this loop. Again, this is miles across, so that means it's hollow. I mean, that means basically you're shooting through a little tube, and so you have to adjust everything so they stay in the tube. We call this a synchrocyclotron, or a synchrotron for short. An example of this is the Large Hadron Collider at CERN in right around the Swiss-French border in Europe. And so this would be an example of a synchrocyclotron. Now, we'll talk more about the applications of these things later. But let's do a couple of examples using cyclotron motion. And I should point out your book actually does cyclotron motion in section 4 rather than section 3. So I'm actually taking this ever so slightly out of order from the book because it kind of makes sense to me to do it this way.